Well, tell me when you're going to start recording.
Oh, I'm already started.
Okay, great. Hey guys, today we're going to talk about what do we call these things? Trig identities.
Trig identities. That's what we're doing.
All right. So
write us the title up there, Mr. Simmons. Trig identities.
Whoa.
Yep, that's what I was afraid of. Erase that. Use this pen, Mr. Simmons. We'll swap.
And the ink flows more smoothly out of this one.
Absolutely. It's a gel pen. That's why. Alright, trig identities.
Okay, the first trig identity goes all the way, well, do we want to start with Pythagorean?
No, let's start with sine,
Oh,
cosine.
that's right. Okay,
Reciprocal.
so reciprocal identities. We know from the coordinates of the unit circle, the sine of an angle is equal to the y-coordinate of that point on the unit circle. And we also know that the cosecant of that angle is its reciprocal, 1 over y. Now, if I simply substitute sine into y, I get an identity. That the cosecant of the angle is equal to the reciprocal of sine. A cosecant is equal to 1 over sine.
That'll work.
Hey,
So I'm thinking cosecant is equal to 1 over sine, and secant must equal 1 over cosine?
It is. Since cosine is x and secant is 1 over x, I can plug that cosine, which is equal to x, into that x, and I get secant equals 1 over cosine.
Very nice.
And likewise with tangent and cotangent, exact same way, cotangent is going to be equal to 1 over tangent.
Alright, so we got cosecant of theta equals 1 over sine. The reciprocal
Right.
of sine is cosecant. The reciprocal of cosine is secant. And the reciprocal of tangent is cotangent.
That's correct.
Interesting. Well, are there any more reciprocal identities?
Yeah, we can actually take this the opposite direction. I didn't leave myself a whole lot of space here. What am I doing? If cosecant and sine are reciprocals, I can express cosecant as 1 over sine. I can also express sine as 1 over cosecant.
I like it.
And of course, I can do the same thing with secant. If secant is 1 over cosine, cosine is going to be 1 over secant. And with cotan,
Then tan must be 1 over
1 over cotan.
So there are 6 reciprocal identities. Like
6
there's 6 trig
reciprocal
functions.
identities, exactly. And we get 6 by taking each one 2 different directions.
Cool. Are there any other identities we might could use? I'm thinking quotient.
Yes, there are. We know on the unit circle that tangent is y over x. But we also know that the y-coordinate is the sine of that angle, and the x-coordinate is the cosine of that angle. So I can substitute sine for y and cosine for x. And you'll notice I'm including the angle with each one of these.
If you don't, it's not a trigonometric
Yes, sine
function.
and cosine are functions, so it's got to be the function of something. Okay. And likewise with cotan, cotangent we learned as x over y, the coordinates on the unit circle. So likewise, I can substitute cosine for x and sine for y. So I have 2 quotient identities.
So 6 reciprocal
and 2
and
quotients.
2 quotients. Is that all the identities we might need to use?
No,
There are
far
more.
from it, even more. Now we're going to go all the way back to
There we go. Just drop us another black in there. Because black is beautiful.
Absolutely. All right, we're going to go all the way back to the unit circle. And we learned the unit circle is not really a circle, it's really a collection of an infinite number of triangles.
That's right.
Where
We use
any-
triangles to make a circle.
Where any point, that's not going to show up, is it?
Mm-mm.
Where any point on the circle,
Go ahead.
okay, we've got a little visitor. Any point on the circle will have the coordinates x and y. And the unit circle we know has a radius of 1.
That's correct.
So we know x is the amount you move to the right from the origin. So that leg of my triangle is x, that's a perpendicular, and that's y. So I know from the Pythagorean theorem, I've got x squared plus y squared equals 1. But I know that x is equal to the cosine of that angle.
That's correct.
So I can replace x with cosine squared and y with sine squared,
Equals
and that equals 1. Now, a little word about notation. It's kind of cumbersome to draw all of these parentheses all over the place. So, as Trig developed, as the notation developed, it evolved into just writing your square,
behind the trig
there.
function.
and it negates the use of having to use parentheses. Because if I don't use parentheses, I'm actually squaring the angle.
Yeah, so you want to square the function, not the angle.
Exactly.
So cosine squared theta
Plus sine squared theta equals 1.
equals 1.
And that is
Alright.
our first Pythagorean.
Pythagorean identity coming from the Pythagorean theorem.
Correct.
All right.
Absolutely.
So are there any more Pythagorean identities, you think, Mr. Simmons?
Well, there's only one Pythagorean theorem.
Right.
Okay? So if I develop any more Pythagorean identities, they're going to emerge from this statement right here. Now, one thing I could do, I've got cosine squared and sine squared and 1. If I divide everything by cosine squared,
Both the left side and the right side.
the left and the right. Now this I can break up into cosine squared divided by cosine squared plus sine squared over cosine squared. I'm running like a kindergarten. Where's my scroll bar?
Yeah, it's right here at the back.
So I had cosine squared plus sine squared equals 1. I divide everything by cosine squared. This giant fraction I can break up into two separate fractions. Now cosine squared divided by cosine squared is just 1. Anything divided by itself is 1. Sine squared divided by cosine squared. Now I know sine divided by cosine is tangent. So sine squared divided by cosine squared will give me tangent squared. And 1 divided by cosine squared, I know 1 over cosine is secant.
Reciprocal.
So 1 over cosine squared will be secant squared.
Secant squared.
Okay. So I have a second Pythagorean identity.
Mr. Simmons, I
That's
noticed
my
you
first
wrote
one.
sine squared first.
Yes,
and cosine
I
squared.
noticed that. And the reason I did cosine sine here is because I had x and y.
So does it really matter?
No. 2 plus 3 is 5, and 3 plus 2 is 5. Although it is traditional to state sine squared first.
Sounds good to me.
And so you've taught this class more than I have. I assume this is usually written as tan squared plus 1.
We can leave it either way.
Okay.
I've seen it both ways, and I'm okay with that.
All right.
So there's only 2 Pythagorean identities then. Well, one main one, and then
Right.
we've derived another one simply by dividing by cosine squared.
But what would happen if I divided by sine squared as well?
That may give us another one, Mr. Simmons.
And,
Drop it, just ready to drop, there you go.
alright. So if I've got sine squared plus cosine squared equals 1, and I divide everything by sine squared, and I'm going to forego my giant fraction. I'll do each one individually. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared, well, cosine over sine is cotangent, so cosine squared over sine squared will be cotangent squared. And 1 over sine is cosecant, so 1 over sine squared will be cosecant squared. So that is our third Pythagorean identity.
That's derived from the main one of sine squared
Sine
plus
plus
cosine
cosine squared
squared.
equals 1.
Very
Divide
good.
3 by cosine squared, divide 3 by sine squared, and you can easily derive the other two.
Now, how's this going to help us? I mean, I see these identities. Identities meaning that the stuff on the left is the
Right.
same thing as the stuff on the right. How would that help us, Mr. Simmons? Let's do an example,
Okay.
if we will. Let's do cosecant of theta times cosine theta. Whoa, that's bright.
Right. Say that again, cosecant
Cosecant,
of theta.
yep, times cosine theta. Now, what could we do using identities to, if you will, simplify this
Right.
expression?
Well, one thing I can do, I can express cosecant in terms of sine and cosine. When we've got these large equations or expressions that we want to simplify, one of a good starting point is to express everything in terms of sine and cosine. If you don't
Sure.
see anything else that's obvious to you. So cosecant is 1 over sine. Okay, and that cosine is over 1. And I use this, what do we call that? The reciprocal identity. I cannot spell.
Reciprocal. Cal.
OCal.
Yeah. All right.
Okay? Now, multiply fractions, multiply numerators, 1 times cosine.
You don't
is
cross
cosine.
multiply?
No, sir.
Oh, okay. I'm just getting that a lot. I just wondered when that would work. Would you like me to take over,
Sure.
Mr. Simmons? All right. So cosine over sine theta. Now, if we remember just from a few flip charts or slides back, we said that cosine over sine is the same thing as cotangent. So, what we know now, and I'm just kind of following down, is that the cotangent of theta is the same thing as cosine divided by sine. So, you can see here how we used these identities to, and here we just simplified by multiplying the numerator times numerator, denominator times denominator. So you can see here how when we started with cosecant of theta times cosine of theta, we simplified this all the way down using identities and just simple math to cotangent of theta. So let's try one more that maybe may not be so simple. Let's try one and see how it works out for us. Let me grab my book here. Got a little something here. So let's try cosine of theta times tan of theta plus cotan of theta. Alright, so we want to simplify this down to one term if possible, like sine or secant or cosine or something. Well, the first thing I know is, the first thing I see is, I can distribute or I can rewrite tan theta and cotan of theta as quotient identities. Now we said that tan of theta is the same thing as sine of theta over cosine of theta. And we said that cotan is the same thing as cosine of theta over sine of theta. Alright, so what we did here was we used the quotient identities. And I'm going to just let ID be for identity. Now, of course, we can distribute our cosine, use the distributive property, A times B plus C is AB plus AC. So we got cosine of theta times the sine of theta over cosine of theta plus cosine of theta times cosine of theta over sine of theta. And all we did here was distribute. So that is the distributive property. Right there, we just distributed. Now if you'll look though, if we're multiplying, we can actually reduce these cosines. So I'm going to reduce those, not cancel them out, but reduce. But if I look over here, there's nothing to reduce on the right-hand fraction. So that's a little more of a problem, but we'll come back to that. So what we now have is sine theta plus cosine. Now cosine times cosine, any number times itself is that number squared. So cosine times cosine is cosine squared theta. The denominator sine of theta is still there. So here all we did was simplify our expressions a little bit. So if you'll notice, we're trying to add two fractions together and they have unlike denominators. That's not going to work. So we have to find a common denominator, something that both 1 and sine of theta is divisible into. Well, I think sine theta will work for both of these. This one already has a denominator of sine theta. This one does not. So how am I going to get this to be a denominator of sine theta? Well, I'll multiply it by sine theta. But if you multiply the bottom by sine theta, we have to multiply the top also by sine theta. So what I'm really doing is just multiplying by sine theta over sine theta times this sine theta over 1. So sine times sine, we already said, is sine squared, just like we talked about with cosine, right? All over sine theta plus cosine squared theta over sine theta. Now the only thing I did here was get a common denominator and add fractions. So we found a common denominator and we added our fractions together. So we're getting there, we're almost done. So if I look at this, anytime we have a common denominator, remember the rule is we can add the numerators together and then I'm just down to one denominator that is the same thing. So this is sine squared theta plus cosine squared theta all over sine theta. But this right here looks familiar, sine squared theta plus cosine squared theta. If I just back up just a couple slides here, we see that sine squared theta plus cosine squared theta is 1. Now the thing about identities you need to remember, the reason we can use them is because they're equal to each other. So anytime I have two things that are equal to each other, I can use either side to represent the other one. So I'm going to go back and we'll finish up, whoops, too far. So we said that what we're going to do here is let sine squared plus cosine squared theta. We're going to use the Pythagorean identity and let this be 1 over sine squared theta. So the only thing we did here is combined our terms or simplified. So now I've got 1 over sine theta. Now if you'll remember several slides back, 1 over sine theta is one of our reciprocal identities. Another name for 1 over sine theta is
cosecant theta.
Cosecant theta. So, only thing we did here was rewrite using a reciprocal identity. Okay? So now you see how we took this complicated thing at the top. If we scroll all the way back up, cosine of theta times tan theta plus cotan theta. We had to go through several different steps all the way down to the bottom where we got our answer as cosecant theta.
So that whole thing is just cosecant.
It's just cosecant. So I can actually go up here, I'll change colors to a white and go up here and say that this is the same thing as, not cotangent, but cosecant of theta. So what we have is cosine of theta times tan of theta plus cotan of theta is exactly the same thing as cosecant theta, and I did that by using these identities that we've learned about. 6 reciprocal, 2 quotient, and 3 Pythagoreans. You're going to have a quiz over this stuff, so you better be studying. See you guys later. We're out of here.
See ya.
No, that's fine.
Leonard is, he's going to be there. And he wanted me to make sure I call Bill Bell.